You
Right.
should be a co-host, though. I'll look into that.
Okay, well, thanks everybody for joining us in the continuation of our virtual seminar series. I'm pleased to introduce Dr. Decker French, who's going to talk to us about bold nuclei in old galaxies. Just a reminder to please mute your mics if you haven't. So Decker did her undergrad at MIT before moving to University of Arizona, where she got her PhD in 2017. From there, she took up a Hubble Fellowship at Carnegie Observatories, where she is now. However, starting in August 2020, she'll be moving to University of Illinois as an assistant professor. So Decker, thanks again for giving us your time, and I'll let you take it from here.
Okay, thanks Matt, and thanks everyone for joining me remotely. So today I want to talk about some of the work I've been doing on understanding the interactions between supermassive black holes and the galaxies that host them. Because this is an interaction that really goes in both directions, in that supermassive black holes are influenced by the environments of their host galaxies and the stars and gas that can feed them. In return, those galaxies are impacted by that accretion energy from those supermassive black holes. And so, making sure I've got my setup correct here. I also want to say at any point, please unmute and interrupt, ask any questions as we go. That's completely fine. All right. Make sure I have my screen. There we go. Okay. So when we think about these interactions between supermassive black holes and their host galaxies, we usually think about the black hole bulge relation and AGN feedback. And I promise that I'll return to that, and I'll get to that later. But I want to start by talking about a different connection that we've been working on for the past few years between host galaxies and the accretion of individual stars by supermassive black holes. So these individual star accretion events are called tidal disruption events. And we can observe these when stars travel within the tidal radius of a supermassive black hole. So as long as this tidal radius is outside of the event horizon, which it typically is for a main sequence star, if the black hole is less than about 10 to the 8 solar masses, we see an observable flare. So here's the nice kind of pretty artish impression of what this looks like, of course, where once the star is too close, those tidal forces can overcome the self-gravity of that star and tear it apart and accrete some of that mass. So what we actually see when something like this happens is something like this. So here is an example of really a prototypical one of these events, PS1 10-Jet H. So this was observed by Pan-STARRS in 2010. And here's what the light curve of this event looks like. So its brightness went up and then down in the UV and optical over the course of a few months. So these are typically found in surveys that are looking for supernovae, since they have fairly similar absolute magnitudes and fairly similar longer durations. So any cadence that's useful for finding supernova is going to be good for finding tidal disruption events that look like this. So these are bright in the UV optical, at least this set, and they have this characteristic time evolution where that power law tail at the end goes as 10 to the minus 5/3. This is what you expect for the evolution with time of the accretion energy. It's not expected that the light would necessarily have to follow that, but at least the first few have been following this 10 to the minus 5/3 time evolution in their optical UV light curves. So a spectrum of this event that was taken right about here, close to peak, looks like this. And one of the things that's been found for these bright UV optical events is that they show characteristic broad lines in their spectra. So this particular event, see, it has a bright blue continuum. This black is the observed spectrum. Once you fit out a black body and some underlying stellar contribution, see that it has these two broad helium lines. So once this event was found and characterized, it was then used as a template to find more such events. So other studies, especially supernova studies like Assassin and PTF, and even in Sloan, people searched and found more of these events. And so here's a set of these events with the, that blue continuum was subtracted off. So here Up top is this PS1 10H event that has the broad helium line. And they all seem to show this. And many of them also have a broad H-alpha, broad hydrogen component as well. So this was the state of things as 2014. I'll show you how much it's changed in a second. But one of the key things about identifying this spectral classification is that we could start to study these events as a population. And that's really useful because we can ask more questions then about these events and how they occur. So the question that I've been focusing on is what kind of galaxies host tidal disruption events like this? And we wanted to parameterize this and study it quantitatively. So the way I think about galaxy evolution is typically in terms of the recent star formation history of galaxies. And so I've been working with this kind of parameter space of recent star formation. So here I'm showing in grayscale galaxies from the Sloan Digital Sky Survey. The y-axis is showing current star formation traced by H-alpha emission. So you can see there's some early type galaxies, some star-forming galaxies on this plot. And then on the x-axis, I'm showing the H-delta absorption. And that's tracing star formation over the past gigayear because A stars with their gigayear-ish lifetimes have very strong Balmer absorption. So you can kind of see, oh, is someone trying to talk? So you can kind of see that there's two different clouds of space in this diagram. It's kind of like a color magnitude diagram where you have this blue cloud and also a red sequence. So galaxies over in this space have been quiescent for a while and they're quiescent now. And galaxies in this space are actively forming stars. So they have that current star formation and also the Balmer absorption. And galaxies over here are galaxies that have had a recent change in their star formation history. They're not currently forming stars at a significant rate and that they don't have a lot of H-alpha emission, but they have this strong Balmer absorption that indicates that at least some point in the past gigayear, they're forming a lot more stars than they are now. So this is where we find post-starburst galaxies or E+A galaxies. And you can see in the Sloan data that this is a real population of galaxies. You can see the group of galaxies that kind of forms this spur. So I've been working on these galaxies for other reasons, which we'll talk about later. But what we found when we looked at the TDE hosts was that on this diagram, you might expect them to lie mostly with the grayscale galaxies, and they very much do not. So this is where the TDE hosts lie in this space. In blue, I'm showing the class of TDEs that has these broad 8 hydrogen helium emission lines, and then the pink crosses are those that were primarily bright in the X-ray. So there's 2 overlaps and 2 new events in there. And they preferentially lie in this post-starburst kind of quiescent Balmer strong spur. So a very different set of galaxies than the normal galaxy population. So what does that imply? Well, it means that the TDE rate in these galaxies must be much, much higher than in normal star-forming and quiescent galaxies. So the set of TDEs I'm showing here was the TDEs found as of kind of the start of 2019 for a recent review that we put out, and about half of all of the TDEs were in what we've been calling quiescent Balmer strong galaxies. So galaxies in kind of this corner of the parameter space. They have strong Balmer absorption and they're quiescent. And the TDE rate in these enhanced by something like 20 to 50 times in these post-starburst and quiescent Balmer strong galaxies. All right, so the big question this raises is why? Because this is kind of an unusual set of things to be connected, right? I'm talking about the tidal disruption events, which are affected by the inner parsec or so of the galaxies, and comparing that to the star formation histories of the broader galaxy environments on kiloparsec scales, right? So what makes the TDE rate so high in these galaxies is really asking, what galaxy properties are influencing the TDE rate. So there's a number of ideas related to the recent merger and starbursts in these galaxies. Many post-starburst galaxies look like they've had recent mergers. This is a really pretty example of a post-starburst galaxy with HST imaging. This is not a known TDE host. This is just a post-starburst that we've been studying prior to the TDEs. And you can see this big tidal arm, and many show these really interesting tidal features. So there's a few reasons related to that triggering of the burst in these galaxies that might cause an increased TDE rate. All right, so one of the first possibilities is that during a major merger that causes a starburst. The starburst is often very centrally concentrated. As you have this gaseous merger, gas tends to be funneled towards the center of the environment. And if you have just a central concentration of stars, it's possible that you simply have more stars available to be tidally disrupted in these galaxies. Another possibility is after the merger, a supermassive black hole binary can be formed. Depending on the separation of that binary, three-body dynamics can come in where a star can effectively be flung from one of the black holes into the other. Basically, these chaotic three-body interactions will increase the TDE rate for a relatively short amount of time during the coalescence of that black hole binary. Basically, once those two black holes are in each other's radius of influence, that will start to give you a kind of a short-lived burst of TDEs over a few mega years or so. There's a number of other possibilities related to some unusual central dynamics in the galaxies. You can set up a centric disk or radial anisotropy and a few other possibilities. And so what we wanted to do was explore the observational signatures of all these different proposed mechanisms for enhancing the TDE rate in certain galaxies. All right, so if there's a central concentration of stars that's affecting the TDE rate, if this is really all just there's more stars there, so more can be disrupted, we expect to find high stellar densities on these small scales. So for the masses of supermassive black holes that we've been observing TDEs around, that radius of influence, so like the radius where the TDEs are going to be coming from, the radius where the supermassive black hole is influencing the dynamics, that's about a parsec for these galaxies. So quite small, but the concentration is likely higher out to larger scales, so they should be correlated. If there's a supermassive black hole binary, we should expect to see signs of a recent merger, like tidal tails and shells, if these galaxies had a recent major merger. Right? And if there's unusual central dynamics that's causing the increased TDE rate in certain galaxies, we should expect to see in their imaging things like non-circular isophotes and generally evidence for an uncoalesced merger in the center. So to study this, we set out to use HST to image 4 known TDE hosts. So we picked the 4 nearest ones, nearest host galaxies for well-characterized TDEs at the time, which was in 2016. Certainly there's a lot more now, but we started with these 4 nearest and well-characterized ones here. So here's what that looks like. So these are Assassin 14Li, Assassin 14AE, IPTF15AF, and PTF09GE. Sorry for all the phone numbers, but these are the 4 kind of nearby events that we studied and what they look like in the HST imaging. So I should say this one in the upper left, Assassin 14Li, this one is a post-starburst. And so not all of them are post-starbursts. This one is a post-starburst, and then these 2, Assassin 14AE and IPTF15AF, are quiescent Balmer-Strong. And then this one over here, it's quiescent based on a spectrum of its center, but you can kind of see that has some star-forming regions throughout. But regardless, this one is not a post-starburst or quiescent Balmer-Strong galaxy. So throughout, I'll draw a number of comparisons of this set to quiescent Balmer-Strong, post-starburst galaxies, but not all of these are post-starburst galaxies, just this one. All right, but all of these have had observed tidal disruption events in the past few years. All right, so what do these look like in terms of their essential surface brightnesses? You can see that for definitely these 2, they have these really bright cores. Assassin 14Li, you can actually see diffraction spikes coming off of that nucleus, which is kind of cool. So if we look at the surface brightness profiles of these galaxies, so the 4 TDE hosts are shown in different colors. Post-starbursts are shown in teal here from a study by Yijun Zhang a few years ago, and early type galaxies in a set of stellar mass matched galaxies are shown here. All right, so we can see that as you go further in, the post-starbursts are generally more essentially concentrated than the early types, which we knew. And the TDE hosts are also very centrally concentrated in the central kiloparsec down to tens of parsec. The TDE hosts are very concentrated compared to the early types. Assassin 14 Li, the one that had that diffraction spike, the post-starburst, is fairly typical of other post-starburst galaxies and has really high central surface brightness. And the other TDE hosts, even though not all of them are really post-starburst, still have these quite high central surface densities, higher than most of the early types. All right, so this is all in central surface brightness. And so they could have high central surface brightnesses for two reasons. One could really be a concentration of stellar mass. The other could be if they have essentially concentrated young stars. So effectively, we want to correct this for a mass to light ratio in case these just have their brightness center because they have more young stars there. All right, so we have three colors of HST imaging. So here I'm plotting the blue minus green color of the 4 TDE hosts. And you can see that many of them, especially Assassin 14 Li, have very blue color gradients. So they're bluer in the center than the outskirts. And this is what we see for a number of post-starburst galaxies. And it's a result of the fact that they have these centrally concentrated starbursts. And so the A stars are more concentrated than the old stellar population. So you have an average of bluer color in the center than the outskirts. And it's likely that the same thing is happening for some of these galaxies. The one that's not a post-starburst or quiescent strong, PTF09GE, this one in pink, this one has a relatively flat color gradient. And then you can see this kind of blue dip. This is from that little star-forming ring that I pointed out earlier. But really we don't care so much about what's going on past a kiloparsec here. What we're really focusing on is what's the mass to light ratio of the centers of these galaxies. We can estimate that from this color. It's not perfect to estimate a mass to light ratio from a color, but a number of the uncertainties in age and metallurgy and dust act in the same direction for these colors. And so those uncertainties aren't as much as one might worry about trying to get any of those individual parameters. All right, so we can use this to get a mass to light ratio and then really plot the stellar mass surface density for the TDE hosts in other galaxies. So this is what I'm plotting here. So this is the stellar mass surface density in solar masses per square kiloparsec with radius. For the early type galaxies, again, stellar mass matched, and the 4 TDE hosts. These dotted lines show the range of uncertainty dominated by our uncertainty in that color to mass to light ratio conversion. So you can see is, even though we're using a single color to do that, we can still tell that the TDE hosts have high central surface densities compared to the early type galaxies. So this is definitely pointing towards this effect being why these galaxies, these tidal surface event hosts, will have had a higher TDE rate than normal early type galaxies. And to explore that a little more quantitatively, we can look at kind of the average density within 100 parsecs. And the TDE hosts have, in general, higher stellar mass surface densities in that central regime compared to the early types at similar stellar mass. So it does seem like the high central surface densities are playing a role in the TDE rate. But there's a few other possibilities that were raised, and there's no reason that these different possibilities couldn't act in concert with one another. For example, you can imagine that a high central surface density would only boost some kind of unusual central dynamics or supermassive black hole binary scenario. So let's explore those. One of the things that was striking when we looked at the images was that these galaxies don't really look like recent mergers. The only obvious kind of merger feature that you can see is not really necessarily a merger feature. In this galaxy, there's 2 kind of big rings, and that could be driven by secular processes as well. These could even be kind of continuations of some spiral arms. These kind of ring galaxies can definitely be excited by secular processes. So we don't see big tidal tails and shells in these galaxies. So we wanted to explore that quantitatively. So to do that, we put these galaxies in concentration asymmetry space. So the asymmetry here is defined by taking the images, flipping them 180, and subtracting that off as kind of a model of them, and then taking the summed absolute value of what's left. So it's the residuals that are asymmetric compared to the total. So there's a few different galaxies that are plotted on here. So starburst galaxies are plotted as these kind of purple little mergers here. These have high asymmetries because there's typically 2 galaxies there. So of course they're not going to subtract off very well. I plot them for comparison because oftentimes what we're looking at is in terms of galaxies that have high asymmetries is late type galaxies. So these are the little spirals in blue, and these often have higher asymmetries than the early types, which are these little gray circles, simply because they have the spiral arms that don't precisely cancel out. So high asymmetry doesn't necessarily mean recent merger. It also means spiral arms. So that's kind of why I'm plotting the late types in this comparison. So you can see that the post-starbursts from Eugene Ding's study are these kind of teal crosses. And these tend to have relatively high asymmetries compared to the early types, these little circles, and also high concentrations compared to them. So then we look at the 4 TDE hosts, we can see that they have very low asymmetries. It matches our visual impression that they don't have these obvious stellar merger features. The one post-starburst, Assassin 14 Li, has a similar asymmetry to kind of some of the lower asymmetry post-starbursts, but certainly the other 3 are below all of the rest of the post-starbursts. So these post-starbursts that are showing obvious merger features are somewhat different than what we're seeing. So that doesn't mean that there's no TDEs in post-merger galaxies, so much that it doesn't seem like you need a recent major merger to have this high TDE rate to explain what we're seeing. There's one exception to this, which is this Assassin 14 Li galaxy. You see that it's not, this asymmetry is not 0. This galaxy is really interesting. It's one of the few post-starburst galaxies that's been targeted with Muse because it had this interesting tidal disruption event in it. It's relatively nearby. And Muse shows something really fantastic for this galaxy, which is that it shows this O3 nebula, basically a Vorwerk. So in this left-hand panel, I'm showing the Muse continuum mission. This is from a study by Prieto et al. In 2016, and it has this bright O3 nebula around it. So here in red and blue, I'm showing the continuum, and green, just focusing on that O3 line. And so this has to be lit up gas. It's likely gas that's lit up by recent AGN activity. And by recent, I mean much longer than the TDE. The light travel time from here to here would be tens of thousands of years. And so tens of thousands of years ago, this galaxy might have had some strong AGN activity or quasar activity. This is probably not lit up by the TDE, since the TDE was only 6 years ago, 2 or 3 years before this Muse image. But we can trace this nebula and look at the asymmetric continuum images from HST, and we don't see a counterpart of this. So whatever is out here being lit up by previous AGN activity doesn't really have a stellar counterpart with a lot of mass. So how do you do this? It's possible that this galaxy might have had a more minor merger in its recent history, maybe 1 to 3, which could explain kind of why it's got some gas flowing out, but not a big set of stellar tails. But it seems like none of the TDE hosts have had a recent, kind of 1-to-1 major merger. Why do we care about the merger mass ratio? It's because in order for there to be a bound supermassive black hole binary by the time we're observing these galaxies, it has to have been a major merger. Basically, mergers that are more minor will take longer for that central component, that second component, to inspiral through dynamical friction. And it is unlikely that a post-starburst that has had a more minor merger would already have that bound supermassive black hole binary. So it doesn't seem like any of the TDE hosts have had a more major merger. So it doesn't seem very likely that the TDEs that we've observed here were affected by a secondary black hole component. All right, the last thing I want to look at is the central components and their isotopes. So when we look at the central ellipticities of the TDE hosts, so we do isotope fitting, start at the center, fit isotopes, and look at how, what their ellipticities are. And most of them are fairly low. We can again draw a comparison to early type galaxies, which are shown in gray here, compared to the TDE hosts. And most of the TDE hosts have relatively low central ellipticities, which is not unusual, on its face. They're, fairly consistent with these. But if unusual central dynamics were affecting the TDE rate, we would have expected the opposite. We would have expected them to have a high central electricity, and we just don't see that. So certainly, this is really only scratching the surface of the different possibilities of how unusual central dynamics could affect the TDE rate. To explore those more, we'll need more than just imaging. All right, so to look at these different observational signatures of why the TDE rate could be so high in post-starburst galaxies, it seems like a central concentration of stars is very likely, and that we do see that the TDE hosts have very high central stellar concentrations on sub-100 parsec scales, and this would explain the rate enhancement in post-starburst galaxies, since the central concentrations we see in the post-starbursts are similar to those we see in the TDE hosts. It seems unlikely that a supermassive black hole binary is causing the increased TDE rate, since given the likely merger histories, there's not enough time to form that bound supermassive black hole binary. And Nick Stone in 2018 has an argument along similar lines about the timescales and how it doesn't seem like this is quite the right explanation. Now, this has the huge caveat, this is the TDEs that we've observed. It's possible that a supermassive black hole binary could, that secondary black hole could impact the accretion of the tidal disruption event and influence what that TDE looks like. So for example, if TDEs around supermassive black hole binaries don't have that same smooth kind of rise and fall of the light curve, if we're not selecting them because they have kind of these unusual light curves that are hard to pick out or just look like AGN activity, we might be kind of missing those. So there's certainly more to be explored here. But at least for the TDEs that we're observing so far, it doesn't seem likely that the supermassive black hole binary is playing a role. And with regards to the unusual central dynamics, it doesn't seem like we can exclude a few possibilities, but to really do more, what we need is spectroscopy, and in particular spatially resolved spectroscopy. So the thing that will really help with understanding the dynamics on these really small scales is something like a 30-meter class telescope. So both GMT and TMT have these near-infrared IFU instruments that will go on that will have, especially being AO assisted, will give us the dynamic spatial result in these very small centers of these galaxies, and will help us actually compare, really compare in detail the dynamics to different models of what could be going on for these galaxies. And that will be very interesting, not just for understanding the TDE rate, but also understanding the evolution of the centers of galaxies as they go through these interesting phases. All right, so we don't have a definitive answer to this question. We've certainly put some constraints on it, but one of the things that we need, in addition to 30-meter class telescopes, is more TDEs. Right, all this was for 4, and certainly there's been more TDEs observed since. We're up to now a few dozen TDEs that have been well classified, and by that I mean they had a spectrum of the event, a good light curve in the UV optical, ancillary data in X-ray and radio, enough data to show it's probably not a supernova, it's probably not EGN variability from a persistent gas accretion. And so to get more TDEs, fortunately, we're about to enter this amazing era of transient astronomy that's going to just take what we have and make it look cute. All right, so until about 2019, surveys were finding about 2 TDEs per year. So between PTF and pan-stars and kind of the start of Assassin, 2 TDEs per year was giving us, a small sample of events. But we're really kind of in this growing regime where ZTF and upgrades to Assassin and Alice are now finding more. So we're kind of still in the ramp up, but we're finding maybe 15 a year right now, but we should start to find more like 20 to 30 per year, which is going to just make the sample much larger. And to give you a sense of what that looks like here, of the 5 nearest TDEs that were discovered with CTF in its first kind of year and a half of operation. So by the 5 nearest, I mean the ones that have spectra of the hosts already. 2 of them were in post-starburst hosts, this 2019 AZH and 2018 HYZ. So all of this is really key to get us ready for the next era, which starting in 2023, we'll have the Vera Rubin Observatory, which is going to find thousands of TDEs every year. So this is going to be fantastic in that there's a number of really cool science things that we can do with thousands of TDEs that I'll get to in a second. But it brings a lot of challenges, namely to do science with the TDEs. We're going to need follow-up spectroscopy to characterize them, multi-wavelength observation to do more science. And so what I mean by 4,000 TDEs per year will be observed, really those photons will be finding us. In order to do science with that, we need to be able to identify those events and classify them in real time, which is obviously a huge challenge, given the limited spectroscopic resources that we'll have. So one of the cool things about this post-starburst and quiescent Balmer-Strong post-reference is, in addition to being kind of a weird puzzle, it actually is a tool that we can use to help find TDEs. And so this kind of intermediate era is an era that we can use to test out these strategies for finding TDEs and identifying them, so that once LSST, the Vera Rubin Observatory gets online, we can hit the ground running and be ready to start classifying those events. So because these post-starburst and quiescent Balmer-Strong galaxies have low star formation rates, the supernova rate is quite low. Actually, the TDE rate is higher than at least the type 2 supernova rate, winds up being maybe comparable to the 1A supernova rate. What that means is that any transient in one of these galaxies is a good candidate for follow-up. So if you see a nuclear transient in one of these galaxies, means it's worth getting a spectrum of it, because it's going to be, if you do this 10 times, you're going to get 5 TDEs. So with, of course, there's a number of trade-offs here between the detections that you'll get, so you can get more detections of galaxies, of TDEs this way. The ability to do this rapidly, so you don't have to wait to get a good light curve to do this. You can do this right away as soon as you know that there's a robust transient, which gives you the ability to get more early time data of these events. This kind of strategy also lets you identify perhaps unusual TDEs. So if a TDE doesn't match kind of the rest of the prototypical example that we have in some respects, but it's in a post-starburst, we might be able to identify things that are outside the mold. So things that have unusual light curves for whatever reason, supermassive black hole binary or something else. The trade-off in that is that you do bias the host sample, right? If we're using a strategy, we're going to wind up with a biased host sample. And so it's important to kind of use this in tangent with other approaches, like what CTF is doing. All right, so this is great. So the problem is that in order to identify post-starburst quiescent Balmer-Strong galaxies, we've been using spectroscopy. So specifically from Sloan and things like that. We won't have that for LSST because of its lack of southern hemisphere coverage, of course, and also just because the redshift that we can detect TDEs out to with the Vera Rubin Observatory is much greater than what we have spectroscopic coverage over. So to kind of overcome this, I've been working on a method to identify likely host galaxies using only the photometry that we'll have in the era of LSST. So only that photometry, as well as, at least in the low redshift universe, Galaxy and WISE data. So there's certainly trade-offs in terms of the purity and completeness of these. Ask me more about this later if you're curious. But basically, the punchline is that we can get hundreds of TDEs per year in the Vera Rubin Observatory era with this method. So over 10 years, getting thousands of well-characterized TDEs is going to be fantastic because we can start to do some really cool science that is basically impossible with the small number of objects we have now. So for each TDE, if you get a good light curve, so here's an example of PTF09G, that same object that I talked about before. This event was caught early by PTF, and so the light curve has a rise and a fall. The shape of that rise and fall is sensitive to the mass of the supermassive black hole. And so by fitting that, something like MOSFET, which is what Brendan Mockler and collaborators have done here, you can fit a black hole mass just based on the light curve. And so if we have thousands of well-characterized light curves from the Vera Rubin Observatory for thousands of TDEs, we can start to get black hole mass functions. And so one of the main features in this plot of, let's say, the rate on the y-axis versus black hole mass is that because that, so I mentioned that you'll only see the TDEs if the tidal radius is outside the event horizon. This event horizon capture will really depend on the spin of the black hole. So the faster it's spinning, the higher black hole mass you can observe TDEs around. So this black line is if in the Newtonian case where there's no event horizon capture, and then these colored lines depend on the spin of the black hole. So we'll be able to make this plot with real data in the era of the Ribot Observatory with these black hole masses. So we can find information not only on the black hole mass function, but also on the spin distribution of these black holes to see what the typical spins are and where this falls here. This is where we are now in making this plot with n equals 12. So we'll go from n equals 12 to n equals thousands over the next decade, which is going to be fantastic to constrain these mass and spin distributions. All right, so I'm going to change gears a little bit, but if you've got questions about what I've just talked about with the TDEs, now would be a good time to ask me those while it's still fresh. Okay, so I'm going to move on to.
Oh, I thought I would just get in one question.
Yeah, go ahead.
So this is Chris. I was wondering, you talked about whether there was any incompleteness if you select with LSST using that you already think they're in the post-starburst type galaxies. So how would that translate to a plot like this, where you would basically, what bias on the black hole mass distribution in those galaxies would you already have?
Yeah, so this is a really good question. And it's one of the reasons that we should do this with the post-starburst strategy and also other strategies. It doesn't seem like the post-starburst would bias the black hole mass function part of this, and that it seems like at least the stellar mass functions of the galaxies are not that dissimilar, except for the kind of the very extreme stellar mass ends. What I do think might be biased for the post-starburst selection is the spin distribution. Depending on kind of when we observe the TDEs in that sequence of merger, if there is a merger, or accretion. I think that it's likely that the post-starburst might have somewhat different spin distributions in their supermassive black holes than normal early types. But I think that the differences that we see is likely to be interesting. Yeah,
I'm not sure the spin will change that much, in their future evolution after this post-starburst phase. Based on the galaxy, asymmetry being asymmetric, so it may not be too bad. Also from the spin side.
Yeah.
Okay. Thanks.
Yeah.
Anyone else before we move on? Yeah, Ariane.
Yes, might be. I'm not sure if this isn't a dumb question, but I'm wondering also about the star at the origin of the tidal disruption event. Does the property of the star may influence what you see? I mean, is there, I don't know if a massive star is easier or harder to disrupt, because that might be also something that would play in your tidal disruption radius.
So this is a good question. For most of the main sequence stars, the mass and radius are kind of conspiring to make the TDE look fairly similar. For giant stars, it'll be different. So there's a few studies by Morgan McLeod a few years ago looking at what happens to a giant star as it gets close to that tidal radius. And because it's so much puffier, it's if you get a grazing interaction, so not just like a kind of an orbit that's taking you like deep within the tidal radius, if you have a grazing interaction, instead of disrupting the star, it can kind of slowly like spoon off different small amounts of mass at each orbit that will look like a much dimmer and longer tidal disruption event. So we wouldn't necessarily even be able to observe that. And it was certainly like very different than the TDEs observed. But for one of the things that we were concerned about for the post-starburst preference was maybe we're just looking at some weird phase of stellar evolution. And so looking at the ages of the post-starburst ages of these hosts, so how long has it been since that recent starburst that we're seeing, seems like they have a pretty wide range of ages. So it doesn't seem like we're finding kind of a cluster of ages right around a certain phase of stellar evolution. One of the things that you can fit using MOSFET is a few of the stellar parameters, but the light curve isn't very sensitive to that, assuming that the star is a main sequence star. And in fact, assuming that that there's not been much star formation in the post-starburst galaxies since that burst, we can try to constrain, what's the most massive stars that are likely to be in these galaxies, and how does that compare to the amount of mass that was accreted? And it seems like those are consistent, such that the amount of mass accreted and what that implies about the star. So assuming like, half of the stellar mass, say, is accreted, we're finding similar masses of the likely stars that were accreted to what's possible from the stellar populations of these galaxies. So most of them seem to be solar mass-ish stars or less, which is consistent with not having really massive OMB stars in these galaxies. I'm not sure if that answers your question.
Yeah, I think it's. I think the answer is we don't really know, because it's if you say that these seems to be solar mass stars, it's if it's a post-starburst, it would be a main sequence star, more likely, but it still could be a giant.
Yeah.
Okay.
In the interest of time, I think we'll just move on from here, and if anyone else has questions, we'll just save them for the end.
Okay. So moving on from the TE, so I want to return to this idea of the connections between supermassive black holes and their host galaxies in what we think about kind of more often in terms of the black hole bulge relation and the implications for AGN feedback. So the black hole bulge relation, which I'm sure especially here I don't have to do a huge introduction for, is this close correlation observed between the mass of supermassive black holes and the velocity dispersion of the bulges that host them. And throughout the years, people have made various, there's been a lot of study done on what could cause this to be so narrow. And there's been various proposals for feedback of that's linking the growth of the galaxies and the black holes, such that the accretion energy from gas accretion on the black hole can act in a negative feedback process with gas in the rest of the galaxy, such that it prevents the galaxy from growing too much compared to the black hole. And so AGN feedback has been invoked then in a number of places of galaxy evolution in involving galaxies from star forming to quiescence. And so what I've been working on is addressing these questions of kind of why do galaxies stop forming stars? Why do starbursts end in this case? To look for the role of AGN feedback and what it might be physically doing to galaxies. As well as how does the gas accrete onto the supermassive black hole as star formation ends. So I've been working on this in the context of galaxies evolving very rapidly. So not very slowly over time, but galaxies that are evolving rapidly after some kind of external event like a merger. So this is kind of the fast track of galaxy evolution, where if you have a gas-phase merger between two star-forming galaxies, you can trigger a starburst that we can then see evolve into a quiescent kind of gas-poor galaxy. So this is one way of transitioning both the morphological and kinematic properties, as well as the gas properties, star formation properties, and as a consequence, stellar populations of galaxies. So I've been talking about post-starburst galaxies in this other context, but this is kind of the main place you might expect to hear it discussed, where we can find galaxies in this intermediate phase by doing something like this. So I've been using galaxies selected from the Sloan Digital Sky Survey that have this lack of current star formation from their H-alpha emission and enhanced H-delta absorption from recent star formation and recent star burst from their spectra. So because these are selected from Sloan, they wind up being in the local universe, redshift 0.2 or less. They tend to be kind of intermediate stellar masses, and they tend to be in all environments. So in mostly the field, but some in pore groups and some clusters. So by selecting these galaxies and using them to study what's happening in their evolution, we can ask a few questions. So I've been focusing on the question of what happens to the gas. So depending on what causes these galaxies to evolve after their starburst, they'll have different implications for what happens to the gas. So for example, if these galaxies become quiescent because the gas is used up in star formation, we should expect to see no gas in the galaxies. If it's ejected or removed from the galaxy in some kind of ejective feedback, either driven by an AGN or star formation, we should expect to see that, and if not the absence of gas, but in its kinematics and state. Similarly, we can look for evidence that the gas is heated or prevented from collapse or something else. Basically, whatever is happening to end star formation after a starburst, it should be visible in the interstellar medium of post-starburst galaxies. All right, so to look at what's happening in the molecular gas of these galaxies, unfortunately, we can't observe the cold H2 directly, but we can observe a number of tracers. So the most common, the brightest tracer is carbon monoxide. So we can look at the CO 1 to 0 and 2 to 1 lines, which are visible in the millimeter. So we can use single dish observations. So I've been using IRAM and also the MCT to observe those. And then you can convert that CO luminosity to an H2 mass. We've also been using ALMA to look at some denser tracers like HCN and HCO+, to trace that cold and dense molecular hydrogen in the galaxies. So our first order question in looking at the post-starburst was, do you need to remove the molecular gas to end star formation? And the answer seems to be no. In this study, we wanted to look at the molecular gas just traced by CO. So this is CO 1 to 0 traced by IRAM single dish measurements. And I'm plotting the CO luminosity, which is proportional to the molecular gas mass in the galaxies compared to the star formation rate. This is kind of like the unresolved version of the Kennicutt-Schmidt diagram, if you're used to seeing that. And for a number of comparison sets, we can see that this forms a tight relation. So we've got early type galaxies in red, star-forming, star-bursting galaxies, and they're well correlated over a wide range of parameter space. But for the post-starbursts, we found gas in more than half of the sample. And even though these post-starburst galaxies have star formation rates that are low, similar to the early types, by selection, they have these high molecular gas masses that are more like the star-forming galaxies. So it doesn't seem like you have to completely get rid of that molecular gas reservoir to end the starburst in these galaxies. Certainly they have less molecular gas than they did when they were starbursts, but they're not yet at the level of early types, which we think that they'll evolve to. I've highlighted just these two galaxies here because they're the subject of a follow-up survey that I'll show in a minute. But I just want to say that even though these are all galaxies in the local in the local universe, other studies have started to see this in the higher redshift universe as well. There's a recent study by Rensus that looked at two higher redshift post-starburst galaxies in the same space, so gas mass and star formation rate, and found that they also lie kind of offset in this diagram where they have more molecular gas for their low star formation rates. So it seems like even though these galaxies are kind of somewhat rare in the local universe, they're representative of a process that's more common as you go higher in redshift. So these two galaxies that are filled in black here, we targeted for a follow-up survey with ALMA to look at their dense gas tracers. We wanted to see, okay, CO might not be the best tracer of molecular gas because it's tracing gas that's not especially dense, all things considered. The HCN is tracing gas that's more than 100 times as dense in terms of the number of collision partners in volume. And so what we found was no detections for both galaxies. And what that means is that the lack of dense gas in these galaxies is consistent with the low star formation rates. So it seems like even though these galaxies have gas that's being traced by the CO, that denser gas is not there. And so it seems like the end of star formation may be driven more by a lack of that denser gas rather than the gas traced by CO. But that has a consequence in terms of the HCN to CO ratio, which is low compared to other galaxies. So that's what's being plotted here, where compared to most of the rest of these galaxies, the post-starburs have a relatively low dense gas total molecular gas fraction. So perhaps something is suppressing that collapse of the molecular gas traced by CO into denser gas that might be possible to form stars. This leaves still another question then, though, of all these post-starbursts that have the CO trace gas. Why don't they look like the early types already? What's happening in the few years that will pass from going from the post-starburst phase to the early type quiescent phase? Where does that gas go? So to do this, we wanted to do a more detailed comparison in time. So not just compare star forming to post-starburst to quiescent, but really look at evolution within that post-starburst phase to see if we saw any trends. So to do this, we wanted to really put galaxies, the post-starburst galaxies, on a timeline. And so we did stellar population fitting on the UV optical photometry from Galaxy and Sloan, and the Lick indices from the spectra from Sloan, to try to constrain the time since the starburst ended in these galaxies. So what we want to do is use this to get kind of a post-starburst age and look at how the gas evolves. So basically making this plot. So we measure the post-starburst age with stellar population fitting. So by post-burst age, I mean the age since the starburst really ended. So the starburst is happening at negative time back here, and we're seeing galaxies then in this post-starburst phase here. And here I'm going to plot the molecular gas to stellar mass fraction traced by CO to see, is there any trend? And so we see on average a trend that's steeper than what we might expect if star formation alone was depleting the gas. Here I'm showing 3 different samples of post-starburst galaxies. In blue, the sample selected from Sloan based on the H-alpha delta cuts I showed before, as well as 2 other samples from Kate Rollins and Katie Alatello, selected in slightly different ways that find more young post-starbursts that are shown in teal and pink here. We find an average trend. In the time scale, this is about 200 light years. Based on the current star formation rates of these galaxies, we might expect a really slow decline as residual star formation consumes gas. It doesn't seem like that can explain this. And even with really, really conservative assumptions about the dust geometry, or assuming that the IMF is extremely bottom heavy, how much star formation could be hiding in low mass stars or dust obscured regions, it seems like we can't reproduce this trend. And so this really points to, I think, something like AGN feedback acting during this phase. There's certainly more work needs to be done in really making that connection. We can point away from star formation, but making that connection to AGN feedback will require a lot more work. All right, there's still a few possibilities. One being anything that we're doing with CO is subject to the CO to H2 conversion factor. So you can imagine, because that is different in starbursts than in normal galaxies, what if that evolves during the post-starburst phase? This like kind of pathological, this conspiracy to make it look like the gas is changing when it's the conversion factor. It doesn't seem like that's likely. One of the ways that we can test this is by comparing the CO trace gas evolution to the dust evolution. So this is work by Joy Lee, who's now a grad student at Caltech. He did this as a summer project, looking at the dust to stellar mass ratio for the same set of galaxies. And he finds the same average time evolution with this completely different tracer. So we don't think that the tracer is to blame. It seems like something physical is depleting the ISM, both in the molecular gas traced by CO and in the dust during this phase. One of the things that will be interesting to study in the next few years is the comparison to simulations and what happens to these galaxies. So there's some recent simulations. So this is from a study by Tim Davis, looking at the molecular gas to, in this case, the star forming gas to stellar mass with a proxy for post-starburst age for stimulated post-starburst galaxies. It seems like they show a similar time evolution to the observed galaxies, which are shown in black. But there's still, I think, some work to be done, especially because the low star formation efficiencies that we're seeing in the post-starburst, the kind of initial question of why do they have this offset in star formation rate and molecular gas, we don't see that in simulations. And part of that is because we can't see that in the simulations. So this is showing the depletion time, which is the inverse of the star formation efficiency. And these post-starbursts up here that have this low star formation efficiency, there's really no counterparts in the simulations. Basically, you can't make star-forming gas not form stars very easily in the simulations. And so there's still some work to be done in kind of trying to model these galaxies, and I think it'll be really interesting to see how we can do that. Because that lets us explore more questions about what caused this. For example, the simulated post-starbursts in this study, most of them had a recent merger, but very few had strong aging activity. So that might mean that aging activity isn't very important, or that weak aging activity has kind of an outside role maybe in the evolution of these galaxies. So certainly there's a lot more work to be done in this, but I think studying the state of the gas in these galaxies as they evolve is really powerful probe of what's happening and what the physical processes are in these galaxies to drive their evolution. All right, so we had these questions of what end the starburst. And we've learned a lot from looking at the gas in post-starburst galaxies. We've learned that it doesn't seem like the gas is simply used up or removed from the galaxy. Right? Something else has to happen to these galaxies. Something's lowering the dense gas ratio. This picture of everything happens before the post-starburst stage, and once the galaxy is quiescent, it's just dead forever. That doesn't seem to be, it seems to be a lot more simple than what's really going on. And when we ask the question of how do these galaxies become gas before quiescence, it seems like at least that CO trace gas does decline to the quiescent levels in a few years. So these galaxies could still become early types based on the observed trends in their CO trace gas, and that any feedback might be acting kind of well after star formation has ended to clear away that remaining molecular gas. So we've been learning a lot about the connections and the co-influence of supermassive black holes and their host galaxies. Namely that the tidal disruption event rate, the rate of the accretion of individual stars, peaks after a starburst. And it's likely that this is due to the high central concentration of stars after a merger. And we've been learning that galaxies can end their star formation after a starburst without losing their molecular gas, and that the role of AGN and feedback might be more complex and might be acting well after star formation has ended to clear away the gas. So with that, I will end and take any more questions. Thanks everyone for attending.
Great, thank you very much, Decker, for that fantastic talk. That was a heck of a lot of information. So yeah, I'll open it up for questions, and just to keep things civil, can you just use the raise hand feature, and then I'll call on you in turn. So Ariane, please go ahead.
Yes, I'm just wondering about the second part of your talks when you try to see if they relate the gas fraction to the post-starburst state of several galaxies, and try to see if there is a connection with AGN feedback. You have mentioned, I think briefly at the beginning, that some of the galaxy that you are studying are in clusters. So that raises the question that does dense environment are responsible to this decrease in the gas density, because there's a number of stuff that can happen in a dense environment, interaction, and finding galaxies that are just clear of that gas. In that sense, I don't think that's the answer to explain why the gas is less dense, but
yeah, so
I mean, you have to take that into account before saying this is AGN feedback.
Yeah, so the galaxies are overwhelmingly in the field and in pore groups. In the sample of galaxies that we studied the CO emission in, there was 4 or 5 that were in kind of denser groups. None of those had any gas. So I think that anything that is in a denser group or a cluster is likely to have totally different processes. So these extreme jellyfish galaxies and some of these post-starbursts and say GASP, those are having something very different happen to them. But these galaxies are overwhelmingly in the field and in these pore group environments. Many of them look like the local group in the future. After the Milky Way and Andromeda merge, will look relatively isolated for being a small group. That's really the typical environment of these. So I think it's important to kind of compare the results of these field galaxy studies to what's happening in the post-starburst in clusters to see how those are different. But certainly something like ram pressure is going to do something very different to the galaxies. Yeah, so I agree.
It's the top of the hour, but I think we can still sneak in one or two questions if anyone has any. If not, I'll ask one. You mentioned how these TDEs are mostly due to sort of the stellar densities in the bulges. Have you considered looking at ultra compact dwarfs, because they've been shown to have supermassive black holes, and I mean there's some of the densest stellar concentrations out there. So can you comment on that?
Yeah, so I think that's really interesting. And I think that any transient that happens in one of these should absolutely be followed up, because it might be a really interesting probe of, you know, especially the black hole properties of this interesting environment. We haven't observed any so far. I think that's likely due to the low rates that, that we might expect, given the number densities of these galaxies. But certainly with LSST, you just multiply everything by several orders of magnitude. It'd be really interesting to, I think, have a dedicated follow-up of any transient in these, but certainly they are likely to have TDEs. It might be the case that even with LSST, the event rate is still maybe like a few per year, but even that would be fantastic. And I think that kind of event would be easily separated out from other transient junk, right? Like the 1A rate is going to be super low in these as well, hopefully. But I think, yeah, I think these are likely to have interesting black hole transients, but we haven't seen any so far.
Okay, thanks. Yeah, no, and it'd be also great if you, in the lower mass regime, if you can start shedding some light on the intermediate mass black hole debate. That would be really fantastic.
Yeah, there's been a lot of work done on what TDEs should look like in these intermediate mass black holes. Some of the plots I showed were from a review paper that were part of this kind of bigger review book that we're putting together through Space Science Reviews and IC. There's one that just came out. I think it's posted on the archive by Kate McGuire on the tidal disruption of white dwarfs by intermediate mass black holes and what that should look like and how to find that. Because finding those events would be, really, really illuminating on the intermediate mass black hole population, since that kind of stellar mass and size to black hole mass regime is going to be easily destructible. It's also got the problem of the rates are low, and the events, the spectra events are hard to characterize. But with LSST, it's still like in the few per year category, which over 10 years is still a fantastic sample. Yeah,
absolutely. Well, thanks. I'll just take one last question from Joanna, if it's quick, and then we'll go from there.
Hi, I don't know if I missed this. I arrived a little late. I apologize for that. But did the the tidal disruption events that are not post-star bursts, did you find that they were also in galaxies with high central surface density?
Yeah, so let me try to pull up the plot. Yeah, so on this one, this blue event, Assassin 14Li, this one is like the bona fide post-starburst. The purple and orange ones are these crescent bomber strong, so not very post-starbursty, but still more than an early type. And then this pink one is not at all. So we don't see anything obvious that would kind of separate them in this space. So I think that even these other galaxies that are not, that haven't had a strong burst, I think that they still do have these high central concentrations. There's another study that was done on larger scales with Sloan data by Jamie Lawsmith, looking at kind of a different parameter space of proxy for black hole mass and Sturzik index. And it does seem like even the ones that, even the TDEs that have non-post-starburst hosts also have these high Sturzik indices. The numbers are still, the numbers in the comparison are still quite small to see what's causing what. But yeah, even the ones that aren't post-starburst so far seem like they have these high central surface densities.
Thank you very much. This was a great talk. Thank you.
Oh, thanks.
Okay, well, thanks again, Decker. That was a fantastic talk, and thanks everyone for sticking around. And I think we'll leave it at that.
Okay. Thanks, everyone.